sir.
Okay, fine. Now I will shift to the inverse Laplace transform and I will continue with the totally from the beginning. So as a definition, suppose if you consider definition of inverse Laplace transform, whatever I am writing that is visible clearly. If not, you can adjust your screen. I think Android you can zoom it. Right now? Suppose if I will use different ink, if Laplace transform of f of t, just we have seen, this we are denoting as a f of s, okay? This we are denoting as a f of s. Then in this case, this f of t is called inverse Laplace transform. Inverse Laplace transform of whom? Of the function, which is a function f of s, of the function f of s. Now the same thing we can write, what I will operate an operator called as a inverse Laplace. If you apply both side inverse Laplace transform, which notation you are using, f small f or capital F here? Yes, anyone, sir, which notation has used? Capital F? Quickly, refer notes here whether your sir using capital F or small f.
Small f.
Small f, that no issue. Okay. Then what I will do, I will take inverse Laplace of the function which is written to the right side, this one. Inverse Laplace of f of s is given by. Now in this case, left side, what happens if you apply inverse, it becomes an identity transformation and you will get a original function. Okay. Whatever notation you're using, that notation you can take. Some author can use capital F, some author can use small f. Okay, f of t. So simply f of t is nothing but inverse Laplace of f of s. Omkar Khote joined. Okay. Now the operator L inverse is called inverse Laplace transform. Now quickly I will take a review of once again the Laplace transform, Laplace transform. You can use your class notes to answer this, and its inverse Laplace transform. INVERSE inverse Laplace transform from this. Okay, you can refer your class notes to answer this. Just a minute, I will insert a table. Now first one. Now instead of that, I will take a big table here. So this one, Laplace transform and inverse Laplace transform. Number one, just you told that, number one, Laplace transform of 1 is equal to 1 upon s. Is it right? Is it right?
Yes, sir.
Okay. In the same manner, suppose if you are writing inverse Laplace transform, what you have to do? You have to take inverse Laplace, means this right side I will write first. So inverse Laplace transform of 1 upon s is given as 1. Okay. Now in the same manner, suppose the second result I will take Laplace transform of e to the power at. Just you have given the answer. Yes, I will take again name. Ankita,
Yes, sir.
what is the answer?
1 upon s minus 1.
S minus a, not 1 in this
Yes.
case. Okay. So that's why inverse Laplace transform of 1 upon s minus a is given as e to the power at. Correct? In the same manner, now I think some condition is there. S is greater than a. That I will not write. That I think you understood. Now in the same manner, similarly, Laplace transform of e to the power minus at is nothing but only you are changing the sign of that constant 1 upon s plus a. This third, inverse Laplace transform of 1 upon s plus a is given as e to the power minus at, opposite sign, remember. Now after that, sine and cos. Suppose the fourth one, Laplace transform of sine at. What is the answer? Yes, anyone? I will take the name who has joined. Just joined. Rishabh. Rishabh, I think. Your class is very good. Huh? Most of the students, they are replying immediately. That means they are attending seriously. Rishabh, okay, your mic is not working. Can you tell the answer? Okay, he may be issue with the microphone. Rohit. Okay, okay. But be sure that for next lecture that your microphone will be working. Rohit Kotkar. Rohit, are you there? Okay, Rishabh. Continue. Rohit. Okay, just I will adjust my camera. Just a minute. A upon s square plus a square you want to say, Ayush, I think. Very good. So sine is given by a upon s square plus a square. Again here I think condition is there. That condition I will not recall. So that's why inverse Laplace transform of. Very good. Okay, it's fine. 1 upon s square plus a square. I will make the adjustment. These are the operator. So this can be written as, what is the answer? 1 upon a, this is a constant, that why I can adjust that term, 1 upon a into sine 80. Now the fifth one, Laplace transform of cos 80 is given by s upon s square plus a square. Am I right? Just a minute.
No, sir.
Just a minute. One note is not working. Once again, I will open it. Yeah. So cos 80 is given by s upon s square plus a square. Therefore, its inverse Laplace is given by. Yes, I can't take outside because this is a variable. Yes, Aishwarya, want to say something?
Sir, actually, L cos 80 is equal to S upon S square minus S square, na?
Okay, Aishwarya is telling that L cos 80 is given as S upon S square minus S square. Can anyone confirm it?
Oh, plus.
It's plus.
No.
It's plus. I'm correct, na? Yes.
Yes, sir.
Yes. You can check. I think Aishwarya would verify it. Huh? Yes, it's plus.
Okay,
Thank
sir.
you. Thank you. So L inverse of S upon S square plus S square is given by cos 80. So here that S we can't take outside, and minus comes for the hyperbolic. So L Laplace transform of hyperbolic. Those who direct second year understood. Sine of H means we are writing this as a hyperbolic sign, and we read it as hyperbolic sign or shine. It is better to read it as a hyperbolic sign 80. And hyperbolic sign 80 is given by a upon s square minus a square. Now again, this a is a constant. I will highlight here and here. This a is a constant. That's why we can adjust. So once again, that L inverse of 1 upon s square minus a square is given by 1 upon a into hyperbolic sine of 80. Okay. Now the same result you can consider for the hyperbolic cos, that Laplace transform of hyperbolic cos 80 is given as s upon s square minus a square. That's why here also L inverse. So we can't take s outside. That's why this can be written as s upon s square minus a square is nothing but hyperbolic cos of AT. Okay. Up to this, I think any problem? Just we are revising. From the Laplace transform, we are taking the inverse. Eighth one, eighth one, I will advise Laplace transform of t raised to n always write in terms of a gamma function. Okay. So Laplace transform of t raised to n is given by gamma of n plus 1 divided by s raised to n plus 1. Again, you can notice this gamma n plus 1 further we can write as a n factorial if n is an integer. Okay. And that is a constant. That's why we can take outside the operator. So this L inverse for L inverse of only the remaining is 1 upon s raised to n plus 1 is given by t raised to n divided by gamma of n plus 1. So further it can be written as t raised to n upon n factorial if this condition is important. N is integer. N is integer. I will adjust the table. If n is integer, both results you can use. So if n is not integer, earlier result you have to use. So ninth one. So this result, I think after the first shifting theorem, I will consider. Up to this, I think okay. So that chart should be in front of you when you are using Laplace or inverse Laplace transform. Okay. So just what we did here, just we are taking the definition of Laplace transform or the result of standard Laplace transform. For that, we are obtaining the results inverse Laplace transform of a standard function. So first one, the linearity property. That property was studied for Laplace transform also. Linearity property. So what this result says? So let symbolical I will write. Let L inverse of F1 of S is some function F1 of T. And so can anyone confirm me whether you are using this notation capital F or small f? I am little bit confused because most of the author they are using capital F. Someone should confirm once again.
Small s, small f.
Left.
Small f, na? Is it fine now? Because what happened, I think Kulkarni sir has taken capital and again I'm taking small, that's why. Okay, it's fine. Okay, thank you. And suppose L inverse of the second one is f of 2 of S, second part is f2 of t. Then the linearity property states or tells us that if you are taking the combination for L inverse of C1 is nothing but the arbitrary constant multiplied by F1 of S plus C2 multiplied by F2 of S. I think same result you have used for the Laplace transform also. What happened? This C1 and C2 are the constant. The linearity property was studied for the differential operator, derivative, everywhere. The same results, the same thing is applicable. So what happened? This C1 can be taken outside the operator into L inverse of F1 of S plus C2 into L inverse of F2 of S. Means what you can do, you can separate the terms. That results or proofs we are not going to see. Okay. So if the terms are given combinedly, that linear combination of function of S is there, then you can use the linearity property to find the inverse Laplace transform. So what are we here C1 and C2? Where C1 and C2 are constants. These are the constant. Now I will take simple examples to explain the linearity property. I think that is clear, but still I will take one example. Suppose for example, I will use a green color to write the statement. Example 1. Find inverse Laplace transform of 1 upon s minus 2 plus 2 upon s plus 5 plus 6 upon s raised to 4. Okay, means what? This is given as a combination, linear combination of f of s. And by applying this linear transformation result, you have to find the inverse Laplace. So for solution, what I will do, the left side I will write as it is. So L inverse of 1 upon s minus 2 plus 2 upon s plus 5 plus 6 upon s raised to 4. Okay, means there are three terms. First term, what is the constant? This is 1. So outside the operator, if you are taking 1, so not necessary to write, because 1 multiplied by anything is always 1. So this is L inverse of 1 upon S minus 2. Okay, plus or minus. What is the second constant? In this case, the second constant is 2. So that we can take outside the operator. So, and when you take outside the operator, it becomes 2. Okay, I am using this result like this only. This one, C1 multiplied by something, C2 multiplied by something. So if you are taking that outside, then the remaining is L inverse of 1 upon S plus 5. Okay, plus for the last one, what is the constant again? Yes, Pratiksha, what is the constant?
6, sir.
6. So why I'm taking name purposely, that means whether you are attending the lecture or not, that I want to verify. Just it. Simple questions I'm asking. So 6 into 1 upon s raised to 4. Now I think the table is with you. Refer that table and tell me. I will take the name. Neeraj,
Yes, sir.
tell me the first. Inverse Laplace of the first term. I am highlighting that. What is the answer?
E raised to 280
E to the power minus means plus opposite sign it will come na
plus 2t.
2t. Very good. Not a. Very good. I'm happy. So plus next one plus 2 times. Next I will take the name Onkar. Onkar Kot.
e raised to minus 5t
Very good. E to the power minus 5t plus 6 plus 6. Now Namrata.
Yes, sir.
What is the answer? I will highlight. I'm asking for this.
T raised to
You want result?
T raised to 3
Yes. Very good. T raised to 3.
T raised to 3 upon 3 factorial.
Yes, 3 is an integer. That's why directly we can apply 3 factorial. But what is a 3 factorial? Ritesh, Ritesh, what is a 3?
6 sir
6. That's why
6
this 6 we get can cancel. So the final answer is e to the power 2t plus 2 into e to the power minus 5t plus t cube. That is the final answer. Okay. I think up to this, Vipul Jadhav has.
सर हॅलो
Yes.
सर 3 फॅक्टोरियल आणि 6 कसं कट झालं
That's why I'm asking ना 3 factorial म्हणजे किती बाळा 3 factorial is nothing but 3 into 2 into 1. This is a definition of 3 factorial, and that 3 factorial comes as a 6. So that's why 6 and 3 factorial get cancelled. I think it is clear, Susmit or Susmit?
सुस्मित सर
Okay, fine. Susmit, is it clear?
येस सर
Okay, fine. I think in the same manner you can consider further examples where simply you can use a linearity property to find the inverse Laplace transform. Now next one, next result is first shifting theorem. Can anyone recall what result you have studied in Laplace for a first shifting theorem? First shifting theorem. Yes, anyone can tell what is the statement?
LF of
Okay,
t
here I will write
is equal
LF of t is f of s then, right now same thing na? Yes, who is that?
I bracket S.
Afia. Okay, next one.
F plus 1, F minus 1.
Not clear. Pratiksha, once again, can you repeat?
Uh,
Laplace transform of e to the power at f of t. I think that's the same thing, na? Make me correct if I'm wrong. And what is the answer? Is it right? Is it right, Ishika?
Yes, sir.
Okay, that same thing we are writing, that same result we are writing in the inverse Laplace also. So here, what is my assumption? If sorry, inverse Laplace transform of f of s is suppose f of t, okay, then then sorry, then inverse Laplace transform, the same result you are writing, inverse Laplace transform of f of s minus a is given as e to the power at into f of t. That result is true for positive and negative value of a. Okay. Now from this, I want to write or I want to make some conclusion here. I want to make some conclusion. The first one, the above statement. So this statement we can write number one. Number one. So how we can write? L inverse of f of s can be written as e to the power minus at into L inverse of f of s minus a. What I did, can anyone guess? I am replacing this f of t by this f of t by this operator only. Okay. I'm changing the position. I'm changing the position also. Okay. In the same manner, second result we can say, L inverse of f of s. Suppose if you are having opposite sign, then what happen? E to the power plus at can be written as L inverse of f of s plus a. Is it clear how I am writing that first shifting theorem as a standard form, that second form? Hope so. I will consider next example. Next, one example I will take, one example I will give homework. Suppose example number 2. Find inverse Laplace transform of first term is s minus 2 divided by s minus 2 bracket square plus 5 square, that is the first term, plus s plus 4 divided by s plus 4 its bracket square plus 9 square plus 1 upon s plus 2 bracket square plus 3 square. Okay. This Laplace transform you have to find. Little bit I will scroll up, means you can see the result of first shifting theorem. Now see, first I will write the given expression as it is. L inverse of s minus 2 divided by s minus 2 bracket square plus 5 square plus s plus 4 divided by s plus 4 plus 9 square plus 1 upon s plus 2 plus 3 square. So first step, what I will do, I will apply linearity property. Means I will write inverse Laplace of three terms. That is L inverse of s minus 2 divided by s minus 2 bracket square plus 5 square complete plus L inverse of, I will keep these two terms together because everywhere the term is given in terms of s plus 4 only. This is s plus 4 square plus 9 square plus L inverse of L inverse of the last one is 1 upon s plus 2 bracket square plus 3 square. I think there is no any issue related to this step. Now next, when you are applying first shifting theorem, you can notice that whatever the expression, this expression given, everywhere you are having s minus 2. Everywhere you are having s minus 2. Means what I will do, I will apply this result. Now see, everywhere you are getting s minus 2, then I will apply this result. I will take e to the power opposite sign. So what it will come? E to the power 2t, and at the same time I will replace s minus 2 by s. That is s upon s square plus 5 square. Okay. Plus next, whose name I was not taken, Mohammad Desai. Can you tell the second term in the same manner by first shifting theorem? Mohammad, fast, big, quick. Mohammad. Yes.
No, sir.
काय लिहिणार? Okay, तो ऍड बंदच केला. No sir, means he is not attentive. Okay, next. Ritesh. Ritesh.
Sir, e raised to minus 4t.
Now see, some students are attending very, means there is no noise, no disturbance, and they are replying. Some students, they are maybe in market or maybe in some other place. E to the power minus 4t, because here you can notice s plus 4, s plus 4, opposite sign minus 4t. So that is taken outside into L inverse of s plus 4 is replaced by s, and it can be written as s upon s square plus 9 square. And the next one, I think Ankita is there.
Yes, sir.
What will come?
E raised to minus 2t.
E to the power minus 2t into L inverse of 1 upon s square plus 3 square. So what I did here? So here I am applying only first shifting theorem. So first shifting theorem. And first one, the result as it is. Now I will scroll up. Now you can refer the table and tell me the standard answers one by one. First, e to the power 2t as it is. So what is inverse Laplace? I will start with the last one. Vipul Jadhav. What is the inverse?
Yes, sir.
This one highlighting the term. What is inverse Laplace of this? S upon s square plus 5 square. म्हणजे s square plus a square चा फॉर्म आहे. पटकन विपुल. ओके नाही सुजान.
Hello.
हा सांगा.
Yes,
हा
cos 5t.
cos 5t. Yes, it is cos of 5t. Very good. Plus e to the power minus 40 into Yashraj. I will highlight what is inverse Laplace of this in the same manner. काय म्हणला आवाज आला नाही. cos 90 बरोबर ना. Make me correct if I am wrong. Plus e to the power minus 2t into next one we will tell. I will take the name. I think Siddesh. Be quick. Siddesh. Okay, Shravani.
Yes, sir.
Can you tell the answer? I think I will highlight, I will square. त्याचा इन्व्हर्स लाप्लास तुम्हाला सांगायचा आहे. ओके, रेड न मी बॉक्स केलाय.
E power minus 2t
हा
cos
येणार का? 1 upon s.
नाही sin 3t.
sin 3t आपण 3 नाही लिहायला पाहिजे. 1 upon a आहे बघा फॉर्म्युला मध्ये. 1 upon a into sin 3t बरोबर का? लिहायला पाहिजे ना 1 upon a. Okay. So what is the final answer? Final answer is e to the power 2t into cos 5t plus e to the power minus 4t into cos of 9t plus e to the power minus 2t upon 3 into sine of 3t. Okay. So this is the required final answer. I think how to apply first shifting theorem, that is clear. So one example you can take as a homework. This is third example. And for HW, now you have to find L inverse of 1 upon S minus 4, its bracket raised to 5 plus, everyone take a note of this. Next lecture I will continue with this example only. I will take the answer from your side. Plus 5 square plus S plus 3 divided by S plus 3 bracket square plus 6 square. Okay. Tomorrow